Oh, hello. These are my solutions to the Chapter 11 homework problems. As you can tell, there's only 5 of them. There's not a ton, but they are pretty lengthy. So I want to make sure that that I take the time to go over them. So you were given this graph. So that is a given. Should write that down. Given graph. And it basically is something we use for all the rest of these. And it's really linking together things with motion and forces and impulse, momentum and energy and work. So this is a fantastic problem for deep understanding and also understanding the mathematical relationships. So if this is our velocity graph, and it told you that the mass of the object was 0.5 kilograms, hopefully you recognize that the acceleration graph is the derivative of the velocity graph. So therefore, this has a slope of plus 10, slope of negative 10, slope of 0. Over here, if we're looking at the total displacement, I'm going to look at the area, which is the integral of this graph, cumulatively. So although we have a negative acceleration here, we still have a positive velocity. So therefore, the slope is always going up. If we have something like this, this is curving up, concave upward, exponential. Here it's curving downward, so concave down, even though the value is still going up because we have a negative acceleration, and here it's a straight line, a diagonal, because we have a constant velocity. And so I figured this out. Basically, from 0 to 2 seconds, the area of this gets me 20 meters. 2 to 3, it's another 15 meters. 3 to 4, it's 10 meters. So the total here is going to be 45 meters position after 4 seconds. This one, what I looked at is I looked at the velocities after 1, 2, and 3 seconds, and I just put that in a kinetic energy formula, and it goes up exponentially, down also that way, that's steep, and then it's constant. For letter D, I ended up having here, this is a force graph. Well, you need to recognize that force is equal to mass times acceleration. That's Newton's second law, great law. And so we already knew the acceleration graph. So this graph should look exactly the same as the graph for A, except that it's multiplied by the mass, which is 0.5. E is an impulse. So impulse is the area of the force time graph. So it's asking for it from 0 to 2 seconds, and anything from 2 to 4 seconds. So this says 3 to 4 seconds, so I need to fix that. And I need to change that to a black text because I can't really read that very well. And we'll see if I want that in bold or not. And then I think I'm going to have this not as nothing. We'll do that as a nice light background like that. Okay. So if I move this down 2 to 4 seconds, yeah, that looks pretty good. I'm pretty proud of myself. So, but it really is happening from, I think it said it's from 2 to 3 seconds is when that's happening. So anyhow, the area of this graph, 5 times 2 is plus 10. Area of this graph, negative 5. So the net impulse would be plus 5 Newton seconds. Now down at this one, it was asking you to figure out the velocity from the impulse, or the change in momentum. So if we have plus 10 Newton seconds as my impulse, this is my impulse change in momentum formula. Impulse is on the left side, change in momentum on the right side. Obviously those two mean the same thing. We think of this as F delta t, or F dt, and this is m dv. We have this quantity from parts D and E, and then we know the mass, so we can find the dv. Well, that dv is plus 20 meters per second, and lo and behold, that agrees with this graph. We went up to plus 20 meters per second. This dt is negative 10 meters per second. And lo and behold, that agrees with this graph. We have a decrease of 10 meters per second. So overall, the increase in velocity from 0 to 3 seconds is 10 meters per second. G is asking about the force versus position graph. Now, this isn't something where there's any formulas for, but we know the force is plus 5 newtons. We know that's happening for 2 seconds. So the question is, how far do we go in 2 seconds? Well, from the area of this graph, we got that it was 20 meters. So in the first 20 meters, we have 5 newtons. The area of this graph during the next 1 second is 15 meters, and that force was -5 newtons. So we have that, and that area is -75 newton meters. This area is plus 100 newton meters. Again, for H, now if I look at that, a newton meter is equivalent to a joule in terms of the work. Plus 100, -75. So if I look at that, I initially have plus 100 joules equals 1/2 0.5 v squared. That gets me 20 meters per second. And then at 4 seconds, plus 25 joules, 1/2 mv squared gets me 10 meters per second. So again, those agree with everything else. I hope you put the time into that problem to think about that the way that it would be necessary. In this case, you've got an elevator. I think it's being pulled upward at 1 meter per second squared for 10 meters. So the work done by gravity is going to be negative because gravity acts down, but the direction of motion is upward. So you could either recognize that that's negative or put a cos 180 there, since the direction of motion is opposite the direction of the gravitational force. This, you need to think about how to accelerate upward at 1 meter per second squared. So that's going to be tension. It's going to equal to mass times the acceleration plus gravity, because we need enough tension to accelerate upward. I don't know what I put parentheses there and not an end parentheses there. We'll see. Maybe I can do that. Ugh. Oh, I don't know how I keep getting those things. Okay. And so that's 10,800 newtons. The work for that, 108,000 joules. Change in kinetic energy is equal to the work, or the net work, so that's 10,000 joules, and that's, I can plug in and figure out how fast we're going. Problem 45 was kind of neat because in this case we've got someone sliding down the hill. I need to figure out the length of the hill based on this height and this angle, so that's just trigonometry. I need to find the speed at the bottom, but my initial gravitational potential energy is going to lose energy due to a non-conservative force done by the wind. But the wind is blowing horizontally and the person is not sliding down horizontally. So we need to find the component of the 200 Newton wind force that is acting against the person's motion. That will be the cosine of 20 degrees. So obviously if the person was sliding parallel to the surface, all 200 newtons, if the person was perpendicular, none of that would end up being against the person's motion. So the cosine is what will be the correct trig function. So this is the general work energy theorem formula. Put in what types of things we're looking at. mgh minus fd cos theta, 1/2 mv fv squared. So that's gravitational potential energy. That's the force equivalent due to the wind, the parallel force, and that's the distance going down the hill. That lets me know I have around 9,300 joules of kinetic energy at the end, and I can plug that into the kinetic energy formula. For number 50, this was kind of weird, but you have this sticky spot here. So you've got this thing pushing up a hill. Spring constant was given. And I don't know if, I wrote that up there. Shot up a 1 meter frictionless ramp, so that's 1 meter vertically, 2 kilogram packages. It's basically designed to load this truck automatically. Find the speed when the package reaches the truck. So again, this right now, you start out with spring energy, but you end up with both gravitational potential and kinetic energy, and it's going around 1.7 meters per second. But if there's a sticky spot on the floor, that's going to be a non-conservative force, slowing the package down, and that's going to be mechanical energy loss due to friction. So I need to use the force of friction times distance to figure out how much of that energy is lost. So that's mu mgd, and that was a 2.94 joule energy loss. So basically what ends up happening here is this ends up with just barely enough where it's not going to make it to the top, because to get to the top of the 1 meter ramp we need 19.6 joules. We've only got 19.56 joules to do that, so it's just barely not going to make it. And if you round it differently, you might say it just would barely make it. Last problem is 57. You've got this person sliding down this hill. I don't know. Sorry for my drawing. Spring, 80,000 newtons per meter, 10 meters above the ground, 50 centimeters compression. You slide down here, slides down here, this is frictionless, and then up here it's not frictionless. It's got a coefficient of friction of 0.15, so you want to know how far the person slides up the hill. So the first thing is figuring out the speed of the person right here based on the spring. So that's a very simple problem. Elastic potential energy turns into kinetic energy, 14.14 meters per second. But then to find out how much the person slides up here, we need to look at all the energy here, subtracting off the energy loss due to this, and recognizing the person's going to end up with some gravitational potential energy over here. So I think about this general equation first, and hopefully you've noticed this, that I've been writing this out every time and in steps, because it helps me think about what kind of energies are involved. So I start off with, at this spot, not just the kinetic energy I figured out, but also the gravitational potential energy. And then I subtract off the work done by friction up this ramp, and that equals the final gravitational potential energy. But now I have to think about the fact that I don't know the height of this. I only know I'm trying to find this distance. Well, friction acts along that distance, so that's okay to say F of friction times d. But to get this vertical height in terms of this distance, I need to do the fact that basically this height is going to be d sine theta. So d sine of the 30 degrees would get me this height value here. So instead of mgh, it's mg d sine theta. So that's my final work energy equation, and there's a lot going on there. To find the force of friction, it's mu mg times the cosine of theta. Why? Because the cosine of theta is the normal component of force. And then that's all multiplied by that distance as well. So this distance is in two parts of the equation, but it's only one variable. So it's just algebra right there. So I plug all this in, blah, 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 and I get that the person slides 32.1 meters up the ramp. So initial kinetic energy plus initial gravitational potential energy minus the work lost due to friction, which is in terms of d, that distance, is equal to the gravitational potential energy, which is also equal to d in terms of that distance. And that's how I got that. Again, hopefully you really spent some time looking through these. We are going to have some practice AP problems and things like that coming up. Take care, and hopefully you have a great day.